Okay, so we're talking about dynamic nuclear polarization.
Also known as dynamic nuclear orientation, but the name changed to polarization recently.
Okay, so you have an amazing new machine. You were going to be testing a ton of different samples, and you're looking for basically changes in weight with these, right? And this is a continuation of your existing mission. You've been working on this for years.
Yeah, it's a pretty complex experiment, and as I understand, we're quite unique in this field. Dynamic nuclear polarization is a process that's been known since the late 40s. Really came out of World War II, the discovery of radar being a life and death situation, so radar was really pushed. Once they had the gigahertz capability, they started noticing that there's these resonances that happen between a static magnetic field and if you ping materials at certain frequencies, different things happen. And it's been used in industry mostly as a spectroscopy, or like learning what a material is and how it is built and how the different atoms connect together to make a molecule and so on and so forth. But based on the work by Frederic Alzofon, who is a theoretical physicist who together with his entire family, saw a flying saucer or some sort of spaceship fly right over their car. So, for them it was obvious this stuff is real, science is missing something, and Frederic went on to try to figure out what it was that they saw over there. And the path led to this process called dynamic nuclear orientation or polarization, which is basically orienting subatomic particle spins in the core of the atom.
Okay, and so this goes back to UFO reverse engineering for you. Like from day one, this came out of the Alzofon experiment, and they recommended pursuing the dynamic nuclear polarization direction. And so this is something that you've been pushing forward for. And as your friend, I know that for the last several years now, you have been studying, researching, seeking out subject matter experts, looking at possible samples to run on this, and putting together an amazing lab. And so this device behind you is just one more aspect of that, right?
Yeah, so the device behind me really got a tribute to this to the great George Hathaway. He, together with Daniel Alzofon, built this machine, and it's a real tragedy. They spent so much effort building it, but they never got around to running the actual test on the sample of their choosing, which was ruby, which we'll get into later. I don't think it was the best choice, but regardless, the machine is set up for rapid testing of multiple samples, and unfortunately they never even ran a single sample through it. They ran out of money and out of interest apparently at the last moment, right when the thing was pretty much ready to go. And it sat dormant for many years. George recently reached out to me asking if I would like to come and pick it up because he saw the work I was doing on the X-band version of this, X-band being like 8 to 12 gigahertz, so higher frequency, higher magnetic field strength. But I always believed deep down that the lower frequencies and lower field strengths would yield better results because at the lower frequencies the energy can penetrate the sample better. Also, the equipment's a lot cheaper at lower frequencies, and it's easier to, you need much larger spaces. You can put in larger samples. You can the sample shape detunes the chamber less. There's a lot of factors that go in favor of a lower frequency, lower field strength experiment, indicating a better coupling that would happen at those levels. So what this is an S-band, or roughly 3 gigahertz setup, and they went to extreme lengths to provide to make sure that the experiment will yield accurate results. They included cryogenic capability. This thing can go down to liquid helium temperatures, which is amazing. That's extremely difficult to achieve. The piping and all the hardware for the cryogenics is on the other side of it. You can't, it's out of screenshot here. Over here you can see there's also a vacuum chamber. So this is done at vacuum in cryogenic environment with an S-band inside of an S-band waveguide. So the amount of moving parts in this setup is astounding. And we're very excited to see what it can do. It should be pretty easy to mount samples onto it and push them into the chamber, pull a vacuum, and we'll be able to run it at cryogenic if we like, liquid helium or liquid nitrogen. Liquid helium is pretty expensive right now. And hopefully we'd be able to discern which samples and what metamaterials are necessary to maximize this effect.
Yeah, and this again is an extension of what you've been working on for so long. So I am just amazed to see it come together, especially with real machinery of this size and scale and precision, as you've mentioned already. That's the thing that blows me away. I think that we're all familiar with little tabletop devices that people have built online, and they're trying to investigate this effect or that effect. You have gone light years beyond that. You are in real world scientific lab machinery. And again, having been at your lab for the last week, this is just one of many large-scale, real scientific machines that you've assembled and you're using, right?
Yes, yeah, very much so. I mean, there's also an X-band machine inside of our Faraday cage, which we've been working with, and it's hooked up to LabVIEW. Like we can control for all the variables. We can see exactly what's going on. And I did a run with that machine, and once I was able to get the sample in the perfect saddle point, so that magnetic field didn't affect it, we saw a positive correlation between dynamic nuclear polarization and then the weight of the sample changing on numerous runs. And of course, I wrote a paper on that together with David Chester, and we went to the Asilomar ENC Experimental Nuclear Magnetic Resonance Conference and presented that there as a poster session. People were blown away by the idea that there can be a connection between nuclear polarization and massive matter. But when they came back to us the next day, they were like, it actually makes sense. Yeah, because science doesn't really know where mass comes from. I know they don't know what creates it. They know it comes from the core of the atom. And nuclear polarization, dynamic nuclear polarization, is the only real way to play with the core of the atom without blowing it apart like in nuclear fission and fusion.
Well, that's an excellent point. And again, having known you for several years now, I have met a number of physicists as well as scientists from other fields who all have different ideas about how this might affect it too. And so then it almost becomes this concept of picking and choosing the best model, but until you have more results and data to work with, I don't think it's necessarily at that point. But would it be fair to say that you've got kind of a plethora, I guess, of ideas to choose from in terms of how this couples to gravity at the core of the atom?
Yeah, that's one of the interesting things about the Alzofon experiment. That's what we call it. So I've shown the paper that Frederic Alzofon published in the AIAA 1981 conference. He was working for Boeing at the time. It was a peer-reviewed paper. He lays out a whole theory. And then there's the experiment, and then there's the dream world of what would happen afterwards, right? And when scientists read it, they tend to look at the theory part, say, no, that can't work because of X, Y, and Z. But then they look at the experiment part, and they're intrigued, and they think about it more, and they're like, that's probably going to work because of my theory. And so far, we're at about 7 theories and counting as to why it would work according to somebody else's theory. But the experiment remains the same. It's still the same thing that we're physically doing. So I'm not really that concerned about which theory is the right one. And I don't think proving it with a positive experiment would even answer that. I think physicists or theoretical physicists will have a field day arguing that, because now they finally have hard data that shows that there's an effect. Now they have to explain it away. But what I'm mostly concerned with is if somebody can tell me, if you tweak it this way, you'll see something different.
Yeah.
predictions like that.
And already you have a couple of major parameters. Again, there's S-band versus X-band, right? And so you have very different frequency ranges that you're applying to this. You also have been acquiring samples from a number of different places.
Yeah, so just to give you an idea of what sort of samples we're talking about, this over here is a aluminum iron mix. This is from the same batch that we saw weight loss in the previous run with the X-band. It's iron powder, 1.5% iron powder, 98.5% aluminum powder mixed in with epoxy. So the individual aluminum pellets or spheres are not really touching each other. They're separated by epoxy that will allow the RF to penetrate better. The idea is with this that the iron particles are more susceptible to paramagnetic resonance and nuclear polarization, but the aluminum can maintain the nuclear polarization for longer. So you kind of use it as a stepping stone. Starting off with the iron getting polarized first, it transfers its polarization to the aluminum, and you're able to build up resonance in that fashion. Another sample that we're trying out is a pellet of osmium, and I might mix this with something else. So what's special about osmium is the densest metal. It's also blue, but it's extremely small and it weighs 1 gram. So if there is a connection between mass and the EPR effect, or the dynamic nuclear polarization effect, having a heavier sample in there will give us a better signal-to-noise ratio. So that's the hope with this. We also have some ruby. This was given to us by George Hathaway, and there's several different pieces. So the reason why he wanted to go with ruby is because ruby has aluminum in it, and also has chromium and some other things that he thought would probably provide a better result. We're going to try ruby at some point, but I don't think it will work as well, because what allows the nuclear polarization to happen is the free electrons are coupling with your microwaves and your magnetic field. And that, in turn, brings a coupling to the core. But when you have a compound, and you have multiple materials that are bound together using those free electrons, now the free electrons are busy. So they're not able to do the coupling like you wanted before. So the aluminum might work great as a pure sample or as a thin sheet of a pure sample. But when it's bound together with something else, I don't think, based on the theory as I understand it, you'd get a very good effect. In fact, most of the samples that are run in industry are non-metals. So I understand why he would want to go in this direction, because that is the inertia of the industry. The industry is mostly looking at biologics. They're looking at cancer cells. They're looking at, let's say Pfizer puts out a new batch of, they had a new recipe to make aspirin, let's say. They're going to send it off to an NMR lab in order to see how pure that is. Now, the NMR lab will stick it into their NMR machine and get nothing back because the signal-to-noise ratio isn't strong enough. So they'll use dynamic nuclear polarization. They'll polarize the subatomic particles in the core of these little atoms to orient and become a more coherent atom. And by doing so, the nuclear magnetic resonance, which is the overall spin of the entire atom, becomes stronger. It becomes more coherent. And then they'll be able to get a signal-to-noise ratio back from aspirin. So we're using the exact same process, but instead of holding a sample in a very tight spot and restricting its motion, we don't really care about the spectroscopy part of things. We're looking at the weight of the sample. And to do that, we have a little force gauge over here, and a sample will be held at the end of the stick. We'll be able to, and it will be free to move up and down a little bit, and just enough to allow us to get a proper weight measurement down to at least 3 or 4 points past the decimal point in grams. So we'll be looking at 1/10 of a milligram change in about a 1 gram sample, which should be sufficient. So far, we've seen In some experiments, we've seen up to like 17% weight loss, albeit they were a bit noisy. But in our more controlled environment, we saw 0.75%, and that was verified over 40 runs. We were constantly seeing these weight changes as it went through the expected point of dynamic nuclear polarization. Now, there are some other samples that we received, such as this one, which is an X-type material. What that means is it's supposedly from extraterrestrial origin, and the layers on this are again of pure metal that are just layered one on top of each other, which I presume would probably yield the best results, because you have all those free electrons that are still free. They're able to interact with the core. They're able to interact with the RF, so we'll get a strong coupling between our RF and magnetic field and the core of the atom. And if we can do that on a small sample, we can do that on the hull of a craft. If you can do it on the hull of the craft, anything that's inside the craft would also be affected by this same effect and become essentially weightless.
Well, if I could jump in, so one of the reasons that you were sent that X-type material, as well as numerous other samples, is you are developing remarkable subject matter expertise. You are rapidly going up the curve in terms of learning on dynamic nuclear polarization. From looking into it myself, it is incredibly complicated. It is definitely a specialist field, and then you're taking that to a new level because, as you mentioned, everyone else is looking at these resonances to measure the composition of materials. You're actually trying to move those materials. That's a completely different game, right?
Yeah, it really is a completely different game, but strangely, it's the same equipment. You just got to drill a hole into it, and stick a string. And I've been telling this to people at the Experimental Nuclear Magnetic Resonance Conference. The response is universal. That machine costs $40 million. I am not putting a hole in it, But I would like to see what you have, to show us next year.
Yeah.
We've been getting a lot of that, and we do plan on coming back and showing the community what it is we've been doing. It's very exciting to be exploring this new region of science. I feel like it's a corner of, some physics labs do have an EPR machine, but most of them are just concentrated on the NMR, where we don't expect this effect to really take place. And it looks like it was a foregone corner of science. It's possible it was already discovered and covered up back in the 50s, back when the heyday of UFO research was happening. And the equipment that was built since then for commercial use of dynamic nuclear polarization is not conducive to running this kind of test. If you really want to run this kind of test properly, you do need to make it mostly DIY, do-it-yourself sort of situation, because the equipment that they sell is not really meant for these types of measurements. They stick the sample in from the bottom, so how are you going to measure the weight? They have cryogenics involved, where it's sitting in a bath of liquid helium, which makes it very difficult. Over here, he went through extreme lengths to ensure that the sample is free to move without any restriction and doesn't have any airflows around it.
Well, so over the next year, as you start to use this machine, right, you're moving up, definitely moving up from a more rudimentary machine that you've tested with in the past. How do you hope to see your results change?
We hope to see a stronger signal-to-noise ratio. We hope to learn what layered materials and what samples work the best. And we hope to learn what processes can be used to make those materials. And through that, we'd know what we need for a full-size fabrication plant to make an actual spacecraft.
Well, yeah, and that brings us back to UFO reverse engineering, right? And I can't stress that enough, because that is one of the things, it's on the website. You have been very open about that as a goal, right? And so there are a lot of other new space startups out there that have, one niche or another. Yours is UFO reverse engineering. That was your inspiration to get into this, right?
Yeah, it really was. I don't want to die on Earth. I would like to be able to travel the stars. I'd like to see that opportunity handed out to many here on Earth. And I don't think rockets are the way to get there. I think there's propulsion technologies that are within our grasp and have been within our grasp for the last 70 years or so that are just being unrealized. Science has either overlooked them, or there's been an active disinformation campaign involved in those technologies. And I think by going open source with the technology, with the experiments, we'll be able to provide, to bring forth this anti-gravity disclosure that we're looking for.
There has been this repeated push, and again, this goes back decades, for the government needs to release this, the government needs to release that. It's people begging the government for things that the government may not have, may not know they have, may not be able to release for whatever reason. It's this back and forth thing. What you are doing is another path. You're saying, we'll do it ourselves, right? Let's build it.
Yeah, there's a saying in Hebrew, like, if not you, then who, and if not now, when? So why not do it now? Why not it be me? And anyone else who cares to join.
Wonderful. Well, Mark, I think that was all I had. Do you have anything you want to talk about? Do you have anything to throw into the mix here?
Oh, yeah. So we're calling it anti-gravity. And I just want to explain to the viewers why it's called anti-gravity, or why Fred Alzofon called it anti-gravity. So nuclear magnetic resonance is essentially something that happens with atoms. You apply a magnetic field, and the nucleus of the atom starts to precess at a known ratio, and you're able to manipulate it, energize it, and so on and so forth. You energize it, and then it pings back down, and when it pings down, it sends out a signal, and you're able to pick that up, and there's your MRI image. Electron paramagnetic resonance is similar, except you're using the electrons precession, which is in gigahertz instead of megahertz. But all of these things, what they share in common is the spin down time. They go from high energy state, they go from a coherent state to an incoherent state, and that depends a lot on temperature.
Okay.
Right, because the Brownian motion, temperature is cooling it up, is basically knocking the spin down, and it has its spin down time or its relaxation time. So with samples, the colder you go, the longer the relaxation time goes. But no matter how cold you get it, even if you're like 0.001 above Kelvin, and they've tried this, there still is a relaxation time. That doesn't make any sense because there's nothing acting upon it except gravity. Now, if gravity is acting upon the sample to make it relax, and you keep it in this oriented state, gravity is doing work to disorient the atom.
Okay.
So by keeping it in its oriented state, you're fighting gravity, anti-gravity. That's why it's called that. It's also could be looked at as anti-inertia, or inertial cooling, or gravitational cooling. We're basically keeping the atom in a coherent state, or the subatomic particles in the core of the atom in a coherent state. And we believe by doing so, we'll be able to negate inertia and negate inertial mass and gravitational mass. And that's why these craft are able to do a 90-degree turn at 10,000 miles an hour, while F-16s cannot.
Well, and it seems like there are a lot of different, so the other day you had written up on the whiteboard something like 4 different approaches to DNP, right?
Oh, no, there's 4 different types of spin that are intrinsic in spin state. So, we'll start off with the most basic, which is subatomic spin. And then there's atomic spin on an atomic level. Then there's electron spin, the spins of the electrons going around the atom. And then there's molecular spin. Now, most of the industry is interested in molecular spin. They want to know, is my molecule what I want it to be? Are the bonds, is it covalent, or are the ionic bonds correct? In biology, they're interested in larger molecules. DNA is technically a really large molecule, strands of different molecules. NMR, nuclear magnetic resonance, is interested in the second resonance, which is the resonance of the entire atom. What we are doing with electron paramagnetic resonance is we're using the electron resonances, which we can manipulate, in order to get to the top nuclear spin state, which is the subatomic particles spin. And by making the subatomic particle spin more coherent, like proton to proton, neutron to neutron within the atom becomes a more coherent spin state. And what this does is, instead of having a whole bunch of spins that are roughly aligned, they all become one. And when they become one, the coupling that NMR gets to the atom, nuclear magnetic resonance, the energy that they're able to impart into the entire atom for imaging or for spectroscopy, goes up by orders and orders of magnitude. We're talking thousands of times stronger signal comes back when you do this dynamic nuclear polarization, where you're orienting the subatomic particles in the core of the atom. So we believe that it is that process of orienting the subatomic particles that is anti-gravity. The nuclear magnetic resonance, the full atom, you're already too big to break the coupling. You're already dealing with too many things. Also, for the word spin, those in the scientific community understand that there's many different types of spin. There's regular spin that we deal with in our daily lives, tire spin, and then there's spin as a term that's used to explain the movement of subatomic particles or the actions of subatomic particles. Now, these are understood through the Stern-Gerlach experiment, where it was first discovered, where they would shoot a silver ion through a curving magnetic field. The magnetic field was shaped kind of like a horn, and the silver ion would either go to the top or to the bottom, and decided those are two spin states. Well, the way we're looking at it in this experiment is the spins of subatomic particles are similar to the spins of macroscopic objects. They're not just it's not just a word like charm or up and down. It's actual spin. Thinking of subatomic particles as electromagnetic energy that's spun in on itself.
Okay. Yeah. Well, and there have been a number of physicists, very reputable physicists. Albert Einstein got very interested in spin.
Towards the end of his life, he was trying to connect, general relativity and quantum mechanics, and he believed that torsion fields or spin fields might provide the answer. And I don't think he was able to, come to complete conclusion of what that answer was before the end of his life. But he turned to spin as the answer. And I believe that the spin resonant states do hide the answer and can bring about the connection between this nuclear, the nuclear world and the physical world that we see, which seem to be incompatible with each other.
Yeah. Well, and again, if anyone is positioned to do this, you definitely are. You're working with subject matter experts. You have an amazing and growing lab. You have some of the best equipment out there, for measuring this stuff. So you are just surging forward on it. So congratulations on that. You were doing it, man.
Thank you. Yes, yeah, we definitely have some of the best equipment in the world dedicated to this task right now. And we're going to put it to good use.